So today I propose to start with the going through the chapter and just reviewing 18.4 and 18.5.
Maybe zoom in slightly. Thank you.
Okay. Like this?
Yeah, that's more than enough. Yeah, sure.
Yeah, great. Okay, so I will try not going maybe too deep into the things. From one reason for that is that I'm not understanding those really deeply. But something if you will have any questions, please ask, or maybe you will have some specific seems to be focused more on. Just tell me and we will try to go a little bit deeper maybe. So
I think that would be perfectly enough. I am having some trouble just getting the surface understanding in this part. So
yeah. So we will try to form the basic structure and relationships between the ideas from those sections. Okay, so basically at the beginning of this 18.4 section, Penrose talks about the locus of the points situated at the r distance in the Euclidean space versus Minkowskian space. And what he says here, he says that in E4 Euclidean space we will obtain a three-sphere, S3. And what happens in M? And in M we will have a different matrix, and therefore we will have different shape with three minuses there, and that shape is actually the shape of the hyperboloid, hyperbolic shape. And basically for different distances that hyperboloid will have different shapes. And basically, for if a or radius of the sphere is equals to 0, we will obtain exactly the conical things like past and future cons there. And if a is positive, we will have those hyperbolic balls like h plus and h minus at the bottom. And if a is minus, then we will have one-sheeted hyperboloid, which will kind of connect the space-like points between those. So it's not non-causal related ones. Okay, let's go, and I just need to take a look at the notes. Yeah, and afterwards he discusses the next thing. He talks about the matrix on those hyperbolic pieces, and he says that the matrix on those can be inferred from the native matrix from the Minkowskian space. Yeah, and afterwards he's talking about the ideas from the chapter 2, and where we have seen already the hyperbolic geometries and the Lambert's idea of the representation of the hyperbolic geometry as the geometry of the sphere with imaginary radius. One moment, I hear that someone connected. Hello, Charles.
I don't think my voice is on. Oh,
yeah, it's on. It's on. It's on.
It?
Yeah.
Did I think I just muted. No, did I mute? Am I still going?
Yes.
Okay, good. Okay, continue. I'm fine.
Yeah, I'm just was wondering, from what group are you? What is your background?
Well, I'm about 71 years old. I've been through all this a number of times, and I'm still working on understanding the, you know, where the getting to the quantum and getting to the point where I can be comfortable with it. And I just picked up a book that it may be able to help me. We'll see. But I'm listening to anything I can. So
Okay,
just go ahead.
okay, got it. Could you please mute yourself because we
I'll
have
have
like...
to figure out how to do that. Just a second. Okay.
Yeah, okay, thanks. So today we are looking at the hyperbolic geometry of the Minkowski space. And basically it's about those shapes, as I have said already. And those shapes are exactly like the ones which will be preserved while going from one reference frame, Lorentzian reference frames, like to another one. So like for two observers, they will kind of see the points situated on the hyperbola, for example, here. Those points will be situated always on that hyperbola. So, for example, if for one observer the event will happen here, for the another one it could happen here. But anyway, if you like switch to any other reference frame, the events situated on the hyperbola will stay in the hyperbola, because like the distance to that in Minkowski space is exactly a, or for example here it's 1. So we kind of fixate 8 equals 1, so we have 1 here. Yeah, so if we'll go back to the Lambert's idea, then we kind of can obtain his imaginary radius sphere by using the conic sections. And
can I just ask a stupid question? What is A?
A is the radius of a sphere. Just the radius of
That's
a sphere.
It.
Yeah, and
it doesn't say what it represents really.
And it represents in Minkowskian spacetime, it will represent the spacetime interval, constant spacetime interval.
Okay.
So basically,
it's like spacetime distance simply.
Yeah. So it will be equal to ct squared minus x squared minus y squared minus z squared equals to a squared.
Right.
And
okay.
Yeah, like for the sake of being, we can just take a equals to 1, and that's all. So it's like a sphere of radius 1, and the sphere of radius 1 will look like that hyperboloid with 2 balls in Minkowskian space. So it's basically a sphere actually. And if you go back to the C4 space, in C4 space it will be kind of a sphere, a complex sphere. And you will work with that as a sphere. But if you take a slice, that sphere will kind of unfold into the hyperbolas.
Right, yeah, I just needed a reminder there. Thank you.
Welcome. Yeah. So, and here, oh, sorry. One moment, I need to put my phone on a charger. Those pictures of hyperbolic geometry representation, like on the plane, and basically that's the conformal representation in which the angles are preserved. And there is another one called the projective one. And in projective, the lines are preserved. So basically the lines in Euclidean geometry will be the lines in the hyperbolic, but in conformal, where the angles are preserved, those lines could be like the circle arcs there, as you can see on the picture here. So those are circle arcs are lines in hyperbolic geometry in conformal representation.
And also the shapes, they are actually the same size, I think. This is just a representation.
Yeah, of course. So like every fish on the picture actually of the same size here. And basically this limiting surface here, we will talk about it today. and it will represent the night sky actually, and basically the limit of like reaching the speed of light. But that will be a little bit later.
But it will never be reached or something, I think.
Yeah, of course. Like for a massive
massive particles,
for a massive object,
massive.
that's true. But for photons, for example, it's they are massless and therefore like traveling at the speed of light. Okay, so the lines we have seen there in the hyperbolic plane representations, where are they here on our hyperbolic surfaces? So Penrose just says that we can take different planes intersecting our hyperbolic surfaces, and those planes should pass through the origin, and where those planes will intersect those balls, in the intersection we will see this a line which will be a straight line in hyperbolic geometry. And to obtain our representations from chapter 2, we need to somehow project our balls to the planes. And here on the figure 10, we have a recipe how to do that. Basically, to obtain a conformal representation of the hyperbolic geometry, all we need is to project on the t=0 plane this upper ball using this this south pole of the hyperbola. So basically you're taking a point -1, 0, 0, you're taking the plane t=0, and you just projecting every point of the ball using just straight lines here to this plane. And you will obtain exactly Poincare or conformal representation of the hyperbolic geometry. And if you will go with another recipe here and you will project from the origin to the plane t=1, you will obtain the projective representations. Okay. Yeah, and basically those lines you see here as the intersections of the ball with a plane, they will go into those circle arcs we have seen in the chapter 2 there. Yeah, also Penrose talks here about different intersections of the cone we could have by the a family of different planes there. I don't remember exactly how the plane was chosen, so it probably should have some. It's a good question, but I cannot answer it now. So he kind of just fixes some special kind of the family of the planes, and basically that family starts with this equation like t=1 and z=1 here. So he kind of fixates everything except x. And if we will have the plane t=1 here, that plane will just cut our conus or cone. Okay, it will cut the cone into a circle, and that's kind of obvious, right? Because cone is cut into circles by horizontal planes. But if you will change the lambda parameter here, the angle at which plane is situated will be bigger, and in this limiting procedure, the circle will go into ellipse, and at some point, and exactly when lambda =0, it will give us a parabola here, so it will be a parabolic section. But Penrose concentrates on the more on metric here, and he talks that the matrix of that paraboloidal section will be flat, and basically it corresponds to the Euclidean geometry. And I'm not sure if he's talking about that here. Probably in the case of the positive lambda, we will have some kind of the spherical geometry, and if lambda is negative, we will have hyperbolas there as intersections. So, like, basic idea is that the different planes will intersect our cones in three different like conic sections, and those sections are like ellipses, parabolas, or hyperbolas. Okay. Yeah, and basically he was doing that to demonstrate that we can obtain like the Lambert representation, like the Lambert sphere with imaginary radius there. But kind of to do that, we need to address the exercise, which kind of just ask us to find those like more rigorous formulas for those conic sections and deduce the metrics on those, just to be sure that we will obtain like the regular Euclidean flat matrix on the parabola, and we obtain a spherical metric on the spherical cone section. So kind of we need to do that to be sure exactly, but at that point I'm kind of just believing that because it needs like a lot of work to be done. Okay, so we have talked about those representation already. Yeah, okay, and basically moving forward, he talks about the H plus as the locus of points which could kind of fix for us future time-like directions for a moving object. And he says that these are simply the possible velocities of a massive particle. And actually, from like remembering the videos we have seen previously on the Chris's channel, for example, we remember that the larger the angle between the time axis and the line, then the larger the speed the object has. So basically, if you will kind of push the line to the right, here rotate it to the right, then the object will have just the bigger beta coefficient, and beta coefficient tells us about the relative velocity to the speed of light. So basically, with beta equal 1, we will be a photon going to the right, and with beta equal to -1, we will be photon going to the left. So it seems that's exactly the argument why Penrose talks about different speeds, like a space, like a velocity space is this hyperbola here. Yep, and he says that we cannot add the two different velocities in the Minkowski space, and basically he talks about the Earth, the spaceship, and a missile ejected from that spaceship with big speeds, like 3/4 of speed of light. And in the Galilean relativity, we will obtain the result like 3/2 speeds of light, but we know that we cannot exceed that. And therefore we need to find like a new recipe to obtain the correct speed of light which will be equal to this like 24 over 25c. And this new formula hides in the hyperbolic geometry also, and basically it like the core of it is this value called rapidity or hyperbolic angle. On this picture we have that angle. Basically, if you have a hyperbola, you can build an analogy with a circle actually. Like if you have a circle, you have this angle here and this arc here, like measured by that angle. And actually the area of that piece of a circle, like small piece, it will be proportional to the angle divided by 2. And the same way it is here, like this area of this curvilinear triangle here, it will be proportional to r over 2. And this arc on the hyperbola will kind of correspond to this arc here. But now, like we don't have this circular scene, and our angle could have the values from like infinity to minus infinity here. And that's kind of obvious from this graph here, where we can see the rapidity dependence on the velocity. So basically it says that like for small values they are actually equal, and we can see this good line like v equals r here. But for the bigger velocities we see that if velocity will grow and come closer to v equal 1, which means v equals c here, if we take c equal 1, it will mean that rapidity will grow to the infinity. And if the object will go to the left, rapidity will go to the minus infinity. Yep. And basically that like velocity addition formula is rooted in the hyperbolic trigonometry. And to do that, you kind of need to understand how we can parameterize the points on the hyperbola using those like hyperbolic angle, that's a hyperbolic angle. And we know that on the circle, we can have points on the circle parameterized by cosine and sine. The same way, the points here on the hyperbola will be parameterized by the hyperbolic sine and cosine. And like the core equation for those is, I don't remember exactly. Probably it will depend on the matrix, but basically here, because time is cosine, hyperbolical cosine, it will mean that hyperbolical cosine squared will be equal minus hyperbolical sine squared will be equal to 1. Anyway, here I should probably show you some solutions to the exercises. So I will jump right into those to show you more formulas. People here, okay. Sorry, a small delay in the browser. Oh, I see a new member. Hello, Mesocosmos.
Hello, hello. Sorry, I forgot this was a little bit different time than usual.
Yeah. Probably Chrome doesn't like a lot of the open tabs here.
I see.
Oh, let's wait a bit. It will come into place. Maybe you have some questions? Yeah, I also have seen that like interesting thing here. Like in chapter 11, we talked about like summing up the rotations on a sphere, and the basic idea there was that like the rotations could also be represented as vectors, but on a sphere. And those vectors should be like identified with big circle arcs on a sphere. Like here we have this like the idea placed. So basically, probably we should start from that sphere. For example, those I, J, and K, they correspond to the different quaternions rotations, like rotation over X, rotation over Y, and rotation over Z axis. And in quaternion world, the same way as in a complex number world, like two rotations should lead us to the like to the opposite point, opposite state of things, right? So like E squared should be equal to -1. And therefore, we have the I rotation on a sphere marked only as like 40, oh, sorry, how much is that? Like 90, right? Like it's like 90-degree rotations here. So 90-degree arc on a sphere will correspond to the 118 rotation in a like real world, in a real 3D space. So basically on a sphere here we have only 90-degree arc, but that corresponds to the P rotation. And if you will go and turn like the object over 2 pi. Well, it seems I forgot about that. I thought I remember the overall process. 2 pi and 2 pi. Yeah, anyway, so let's just pass it. I just wanted to say that I don't understand that in a hyperbolical sense, but now I understand that I forgot the sense in the just like plain Euclidean one. Okay, so let's just jump to the exercises. It's number 8. Yeah, probably number 8 is a great one. So basically here we can see really like interesting argument about this the system of the Earth, spaceship, and a missile. And the author here, he's talking about that like at the time t, the sphere of the like if we emit a flash of light when the spaceship takes off from Earth, the light expands spherically in both the Earth observer's coordinates and the spaceship's coordinates. So we will have like two situations. Those unprimed coordinates are for the Earth observer, and prime coordinates are for the spaceship observer. And all of those should be related between themselves as linear functions, because if they are not linear, then observers will kind of see some kind of the fictitious force we see in the accelerated frames of reference. And therefore, like x prime should depend on x, y, z, and t only in linear fashion. And like the author here, he says then, therefore, we should have some kind of the proportionality here between two systems, those like space-time intervals. And because of the relativity principle, we should have the similar identity, but with the coordinates swapped. And therefore, we will obtain this like preservation of the time space-time interval. And afterwards, he just drops like two coordinates and jumps back into much simpler case with one spatial and one time coordinate. And on H plus, we will have this interval equal to 1. And afterwards, he says, let's just mark the time coordinate using cosine hyperbolical and our x as sine hyperbolical. And afterwards, we will obtain like our speed as a tangent, hyperbolical tangents there. And also, we will have this equation also. And afterwards, he just shows the space-time diagram from the Earth observer, and he says that like the same those lines, like those hyperbolas, they will be like the lines of simultaneity from his perspective, and basically at that point of time, E, the spaceships will be here and the missile will be here, and those angles like r and lambda, they will be determined by the relative velocity, like by the beta coefficients probably here. And to add the velocities here, we need to add those angles. And to understand that, we need to understand that like the Lorentz transformations are basically the hyperbolical rotations. And hyperbolical rotations are of that form. And we kind of will have like two of those there. And after multiplying everything, we will have that matrix with the added angles here. And by knowing that velocity equals to the like hyperbolical tangents, we will obtain that formula, which kind of more easily to see if you take a look at this screenshot from the Chris's video. So you can see the formulas for the sum and difference of angles at the bottom of this frame. And you can see that if you divide like sine over cosine here, then and in the denominator we will have this cosine of product plus like sine's product, and if you divide everything by that cosine product, you will have 1 plus product of tangences, and on the top you will have sum of two tangences because cosines will just cancel out. So basically we will obtain the familiar formula that to add two velocities you need to add those and divide over 1 plus the product of those velocities. So or in case of C1, those are just beta coefficients actually for different frames of reference. So basically the velocity addition is actually comes from the hyperbolical trigonometry and from basic identities there. There is also like one more way to go here. Probably I've closed that solution, but anyways, there is like one way to go. Like you can work with the standard Euclidean trigonometry and afterward just swap the signs. Yeah, but anyway, probably we should go further. Yeah, there also was like more simpler exercise where Pedro was asked to derive the formula for V from this formula for rapidity, and basically that's done here. It seems pretty easy for me, so you just kind of exponentiate everything, then put like everything connected with V to one side, with R to another, divide everything by something good enough, and you will obtain the needed formula. Yeah, but like those logarithmic or exponential representations come from the fact that hyperbolic trigonometry functions, as well as actually standard sines or cosines, could be represented using the exponentials. Yeah, and that moment of the equality of the rapidity with the velocity could be explained using this equation. So basically, if you will take a derivative of the r over v, dr by dv of that function of logarithm, you will obtain this 1 over 1 minus v squared, and which is just the sum of the geometrical progression here. And we know that v is less than 1 here, so we can just expand that into this infinite sum 1 plus v squared plus v to the 4th power, and etc. And afterwards we can just integrate it over, knowing that r equals 0 for v equals 0, we will obtain this result, like r equals v plus some small number, which basically doesn't matter in the case of small velocities. So that's kind of the proof for the equality between v and rapidity. So to sum up this fourth section, it talks about that like the basic geometry of the Minkowskian spacetime is a hyperbolic geometry, and we can obtain different Euclidean representations of that geometry by using the projective procedures like described on that picture, where like hyperbolic lines are just intersections of those balls with the planes. And also talks about like velocity addition here and the importance of the hyperbolic angles in that case. So that's like the overview of the main ideas of section 4. Any questions? Because I'm going to jump into section number 5. Okay. Sorry. Yeah.
Enjoy the rest of the call. I have to leave.
Okay. See you, Chris. Bye.
Bye.
One moment, guys. I need to pour a glass of water. One moment. It's bad that Chris is gone. I actually wanted to, like, for him to know some things I will talk about in this section. But anyway, so here at the beginning of the section 5, Penrose starts with considering the hyperbolic boundary of our hyperbolic representations while doing that projective procedure here. And basically we should remember here that actual space-time is 4-dimensional, and therefore those planes, they are not 2-dimensional. Actually those are 3-dimensional Euclidean spaces. And basically we are projecting like 4-dimensional subspace, like, sorry, 3-dimensional hyperbolic ball sitting in the 4-dimensional Minkowskian space to the 3-dimensional cube here. So basically we will have a cube, like Euclidean 3 space, something like that here. And therefore, like this circle here is not a circle actually, it is a ball. And because it is a ball, its boundary is a sphere. And it's like the usual sphere we see like in the daily life S2. Yeah, and like this boundary describes, as we have said already, the unreachability or unattainability of the speed of light by massive objects or particles. Yeah, and that speed, that like boundary, could be attainable only for photons. Like where we see a lot of photons in our daily life. And here Penrose answers with the question that it is a sky at night, that basically watching the stars is absorbing the photons, right? And he says if you will imagine yourself in the outer space, you will see the whole S2 boundary as the light coming to your eye from the distant stars. So basically you're kind of able to see that boundary of the projected light cone.
From all directions.
Yeah, from all directions, right. So basically it's because, as far as I understand, it is kind of like two-dimensional sphere wrapped over you in three-dimensional space, and it is a projection of the three-dimensional light cone lying in 4 dimensions. So that's like the situation we are in. And he afterwards talks about like, can we induce some kind of structure to that like celestial sphere, which is actually a boundary of our hyperbolic geometry like representation. And he kind of trying to slice somehow the light cones or hyperbolas to obtain a sphere. But afterwards he's saying that for different observers, like for observer at rest and for a moving one, we will have like a different representations of the celestial sphere. Yeah, and he says that it was already known in the 18th century and was observed by James Bradley and called stellar aberration. And according to this effect, the apparent position of a star on the celestial sphere is seasonally slightly displaced, owing to the fact that the velocity of the Earth changes when it is at different places in its orbit about the Sun. And to explain it in more simpler terms, he addresses here like the driver's example, which I call it like if it's raining, and like for the observer at rest standing on the Earth, the rain falls downwards. But if you're traveling on the motorcycle or you're traveling inside the car, speed of the car is like a lot more faster, and therefore the rain for the driver is kind of has a more horizontal velocity, and therefore it kind of goes into your car glass like straight ahead horizontally more. And that's because like the car velocity is a lot bigger than the rain velocity. And the same principle works also with Earth's velocity and the stars. And by stars, I mean the speed of light which is coming from stars to the Earth. And because the velocity of Earth is not that great comparing to the velocity of light, that like aberration effect is really small. It's only 20 seconds of arc, in fact. It means like if you have a degree, I mean like 360 degrees in the circle, or 2 pi, right? Then those 20 seconds is just like, I don't remember exactly, but it's just one part of the degree, like really, really small quantity over the circle. but nevertheless, the effect is present, it's measurable, and it represents a velocity-dependent distortion of the celestial sphere, and that is telling us that we cannot regard this sphere as having a natural metric structure independent of the velocity of the observer. So basically, the distance between stars will depend on the velocity of the observer. But Penrose wanted to have some kind of a structure universal to any observer, and he addresses that using the Riemann sphere. Yeah, I just want to try to recall how the Riemannian sphere is connected with this thing. Okay, so probably here Penrose just talks about, like, remember in chapter 8 we have seen the Riemannian sphere, and the transformations of Riemannian sphere, they are conformal, they preserve infinitesimal shapes, they preserve circles, sometimes converting those circles to the lines, like in the special case, right? And it always preserves the angles between curves on the sphere. And afterwards, he says that accordingly, like, our celestial sphere also could be interpreted as the Riemannian sphere, actually. And he says that accordingly, any circular pattern of stars as perceived by one observer must also be perceived as circular by any other. And this suggests that there exists a really convenient stars labeling. So he give no proofs here, but he's just how to say, he just states that there is a conformal structure on the celestial sphere, and celestial sphere could be interpreted as a Riemannian sphere, and therefore every star could have a label which actually is represented by a complex number, allowing also infinity there. And basically, like, every star could be placed on the complex plane and then mapped onto the Riemannian sphere there by the same procedure we have seen in the chapter 8. But afterwards he says, but will not we have some problems because of the lens contraction? We know that relativity theory predicts this flattening effect. So a sphere traveling along us or aside of us, right, with a big speed will shrink. And he says, why not the circles on the celestial sphere, why they will not shrink? Why circles on the celestial sphere will be preserved? Sorry, one moment. I see that someone was writing something in the Discord. I want to check this out. Oh, great. Chris just shared his video with everyone. Oh, I see more people. Let's welcome they also here. Hello, Mista and Nate.
Hey, Slava. How's it going?
Yeah, everything is fine. How are you? How is your progress?
Oh, I'm good. I messed up the time change.
Oh, and I was trying to warn every one of you, but it was 2 weeks ago.
You are not the only one.
Okay. Yeah. Anyway, I hope that you haven't missed anything really important. If you have any questions considering section number 4, just ask those, and like after we will end with section 5, okay? And Nate, hello, how are you?
Good, doing well. How are you?
Great, great. And have you read the chapter 18 also?
Yeah, I wasn't able to reread it this week, but I read it a few weeks ago, yeah.
Okay, great, great. You have also had the same mistake with timing today.
More just a little busy. Have some errands that I've had to do, so I was a little late. But...
Got it. Okay. So please ask more questions after we will end the section 5, if you have any. Anyway, so that's really amazing fact. Basically, one of which I'm amazed the most while reading those 2 sections is that this flattening effect, the length contraction, is actually not directly observed. And at that place I was like really surprised, because every book or every video I have seen about special relativity, they kind of talk about it as it is, like it's kind of implicit that it should be observed, but actually that's not observable to us. And that's comes from this picture where Penrose talks that kind of fast traveling object and the light which will travel to our eye from that object, like those shrinking, that shrinking will compensate exactly between the difference in the distance which light should kind of cross, depending on the placement on the object, like the rear side or the front side. I do not understand that deeply, that's true, but anyway, even as a statement, that's kind of really wondering, or like really amazing for me. So at this moment I just want to address that using some Wikipedia pages. So basically, if you will go to the length contraction Wikipedia page and you will take a look at the visual effects section there, you will be directed to the terrestrial rotation article. And basically it says that we cannot directly observe the length contraction by our eyes. And if you go to the article about telerotation, you will see this beautiful GIF that while contracting, the visual appearance of the object will be as like it is rotating. So basically, with small contractions, we will see just a rotation, and with small, like special, with small sizes of object, as far as I understand. But if they are bigger, you can see this like a little bit squashing or like shearing. I don't understand the exact transformation here, but you can see that the front side is curved and is longer, and the rear side is curved and is shorter a bit, and the whole object is rotated for you. So it's kind of really interesting, and if you're interested, we can kind of take a deeper look next time onto that matter. I just haven't had enough time to read a lot of articles about that, but we have different interesting articles explaining the visual appearance of the rapidly moving objects, and I can just send those to you and we will read those together, for example, for the next time, if you're interested in. But anyway, it's really interesting fact. Yeah?
I don't know if people, but in chapter 18 I posted a tweet. A tweet shows, you can see this visually, like an animation that somebody made.
I haven't heard you really well, but as far as understood, you've been talking that you have shared some tweet about this.
Yeah, in chapter 18 on August 8th, so there's a tweet I put on from Berger Dillon that has like an animation of this idea that you can't really see the length contraction. It's a pretty good animation, I think.
Let's take a look.
I posted it in the discussion.
Maybe you can explain that for us. Because I'm not sure that I understand that. Okay, meanwhile, any questions? Maybe Joe or you and Nate, maybe you have something to ask about the section 4.
Karkunov, if you are talking anything, we can't hear you.
Ah, sorry. I was muted all the time.
Yep.
A couple of minutes.
Oh, sorry. Yeah, I've been talking. Sorry. Yeah.
I just realized.
Yeah, I just, first of all, I asked Nate to maybe comment a bit about that animation. Like, what's happening here? I don't understand exactly.
A general question, is this length contraction observed in general relativity?
Yeah, it should. Yeah. I mean, it should be, but it is probably not observable by eyes.
Well, I think it's not observable to like a human eye, but you can do it with interferometry experiments. Like if you had, two arms of like a Michelson interferometer or something, where the two arms are perpendicular to each other.